Our next talk is from Sampath, from the Indian Institute of Science in Bangalore, and his talk is electrochemical interfaces, molecular assemblies, and materials towards energy conversion and storage. Welcome, Sampath.
Thank you very much, Holmes, for the introduction. It's a pleasure to be here. Let me thank the organizers, particularly Professor Cheetham and Professor Sena Rao, for the invitation to be part of this meeting. What's going to happen in the next 35 minutes is to look at some interfacial properties, particularly on the electrochemical interfaces. Electrochemistry is a subject which has been there for a long time, 18th century. And people generally take it for granted in terms of what happens at an interface. But the interface is not that simple. What I mean by saying interface is essentially an electrode-electrolyte interface. It could just be a solid-liquid or a solid-solid or even a liquid-like liquid interface. And many of these interfaces, if you look at, if they have some conductivity, at the interface you will have a huge electric field. The electric field is in the order of about 10 power 7 volt per centimeter. That's really huge. And that's one of the reasons as to why the electron transfer takes place between a species which is moving around in the solution with an electron on the electrode surface. It's pretty complex. I'm just going to say something on the recent findings. In this particular case, some examples from the literature and also one of our studies as well. And this is more like a motivation for what I'm going to talk about a little later, particularly on electrochemical reactions and the surface pressure, where I would talk about carrying out electrochemistry on molecules at the surface level, but not dipping the electrode in the solution. And then something to do with inorganic electrode materials, and then if time permits, and possibly go on to the assemblies of phthalocyanins and things like that. The interface, as I just mentioned, is solid, liquid, or liquid-like liquid. It's been, it's there all over. Wherever you have a heterogeneous system that's looked at, you have this kind of an interface. And many of these applications that I've just mentioned down do have this kind of an interface. And the interface, if you really look at, back. Okay. Interface, if you just look at on the right side, you have close to the electrode surface, you also have something that's getting onto the surface as a film. So these kind of interfaces do have issues not easily understood. This is what is known in the literature. This is a textbook material, as you see, right from Galvani in 1771, followed by Davy and Faraday. The interface was not really understood completely, if you really look at it. Helmholtz was in 1853 when people started talking about the interface. And at the electrode-electrolyte, you have what's given on the left. You have certain sections of ions and solvent molecules that are actually organized in a particular way. Very often what's understood is that you have anion that's coming onto the surface. It's called specifically adsorbed anion. Even on a negatively charged surface, it can actually get adsorbed, followed by partially solvated ions and all other things. So essentially you have a thickness on the electrolyte side which compensates for the charge on the electrode surface. This is what is understood, and this is what is there in the textbook. And there have been quite a bit of changes that are looked at, right from Stern, Graham, and Bockres, Devanathan, and then subsequently all others as well. But then it is not as simple. I'm just going to give you a few examples. This is one of the papers. I'm sorry about the references. This is PNAS 2022. There's a little resolution problem here. This is a paper from Mark Koper from Leiden University, which was published in 2022. If you really look at what's written here, a platinum electrolyte interface, which is known to be something very simple and 1-1-1 surface, a single crystal surface, it should be something very easily understood. But that's not. It doesn't really follow what he says is a Gauss-Chapman-Stern behavior. On the contrary, you have water molecules which are very close to the surface, which changes the orientation on the electrode surface, which actually leads to lots of other issues in terms of what happens at the interface. So this one was sort of, again, I'm sorry about this. Let me just tell you what it is. What you have here is all capacitors, and there are two capacitors which are in parallel, which is in series with another capacitor. Typically, an electrochemical interface is understood as a capacitor. It's nothing but you have a conducting surface, on the other side you have another conducting surface, in between you have a sort of dielectric. But then what the Cooper and the group has found is what's given here, where the interaction is slightly different from what you exactly see, which is based on the Gauss-Chapman layer. And this is another study where water structure close to a surface being very different. This is something that we have been actually looking at. We work on electrode materials which are not very highly crystalline and smooth. Most of what's understood in the literature is all based on nearly atomically smooth mercury surface. But then when we try looking at polycrystalline surface and also a little roughness, you have lots of heterogeneity on the surface, which leads to what I have just given here as a gap close to an electrode surface, which we call as a hydrophobic gap. What does that mean? It actually gives you solvent characteristics which are very different from that of the bulk. Even though I have the electrode in the bulk of the solvent, water, very close to the electrode surface, things are slightly different. And that is understood based on what I have just mentioned as the capacitor and series. And this is one example where water structure is actually looked at close to a surface. This is based on electrochemical atomic force microscopy. So what you're seeing here is the electrode surface, and then you're just going into the bulk of the electrolyte. And look at the dielectric constant of water. It's close to about 25. And after about a few nanometers, 1 or 2 nanometers, it reaches a bulk value of 78. And this happens on an electrode surface very often because the surface has heterogeneity associated with that. And in this thickness, water behaves like an aprotic solvent. Essentially, one can stabilize radical anions, for example, in aqueous medium, which otherwise is not possible. And what you see on the other side is a control experiment wherein you do have a hydrophilic surface having more or less the kind of dielectric constant that one would expect in the bulk of the solution. So the surface matters a lot in terms of what happens at the interface. There's one another example to say interface is important. You see in most of the fuel cells and electrocatalysis, we encounter what we call as a solid-liquid gas interface. Essentially, you have in a fuel cell, the gas is actually coming from outside. Then you have a liquid, which is an electrolyte, and also solid, which is an electrode. So you need to have a three-phase boundary. And the three-phase boundary is the one that makes a huge difference in terms of understanding what happens at the interface. And this is something that goes back to the lithium battery. The lithium battery that we're all using comes out for about 500, 600, 700 cycles simply because of this particular aspect called solid electrolyte interface. When we charge and discharge the battery, we essentially have a film that gets formed on the surface, which is ionically conducting and electronically insulating. And this was proposed by Doron Arbach and Pellet in Bar-Ilan University several years ago. And this is what is responsible for the lithium batteries to work for a large number of cycles. The last example is related to, I'm sorry about this figure again, this is related to the gas evolution. There's plenty of interest in hydrogen, oxygen evolution, and water splitting and all that. So whenever we have such gas evolution happens on the surface, the gas bubbles actually get nucleated on the surface, they grow and they coalesce, and gas evolution happens. This also affects the kinetics of electrochemical reactions. So one needs to understand whatever happens at the end in terms of efficiency with all these things in mind. So this is just to kind of give an idea of why interfaces are important, and particularly in recent times, which can't be explained based on the traditional Gauss-Chapman theory. With that, I'm just going to go on to two aspects, and I shall talk about electrochemical reactions and the surface pressure. This is essentially based on certain confinement of molecules, and the molecules are in close proximity with each other, and they all have a nice orientation. So when I have this condition satisfied, it's possible to have electrochemical reactions which are giving slightly different products and different kinetics and thermodynamics as opposed to what one has in the bulk of the solution. People have been actually looking at this kind of interfaces for quite some time. You see some of these examples. The top one is actually the effective surface pressure on insulator to metal transition on a Langmuir trough. So on a Langmuir trough, if I have a polymer, compress it at the interface, you start to see this transition. And then what you see on the right is actually the nanorod to nanowire reactions again at an interface. And the interface that I'm talking about is actually a liquid air interface. And there's one more from Majda's group. This is one of the classic papers, I would say, on looking at the electron transport across monolayers. So these are some of the things that are known in the literature before we actually got in. And our interest has been looking at electrochemical reactions at the interface, not just this. I'm going to take one example of this and then explain to you what it is. But then we have interest, for example, like amide bond formation without any coupling agent. So you have a carboxylic group and an amine, and it gets attached to each other at the interface, and you form an amide bond, probably leading to the protein formation and things like that. So essentially, our system contains it's a Langmuir trough wherein we have a molecule stabilized at the water-air interface. The moment I just have this kind of a surfactant, you have them having all kinds of orientation, and I start to compress them at this surface, and they start to have a little interaction, and subsequently you start to have a solid phase. So this pressure area isotherm is something that we would be able to follow and understand what exactly happens as far as the pressure is concerned. What you see on the right is the properties of such monolayers. Why is it that we look at something like this? The proximity effect, and they're all in close proximity to each other, and nice orientational order, and the surface pressure that we talk about is of the order of gigapascals. I just mentioned earlier that the electric field that you have is of the order of 10 power 7. So in addition to that, you have another parameter that helps us in controlling the kinetics and thermodynamics of this. I'll take one example and then explain to you what it is. In this particular case, I'm just going to polymerize aniline. It's polyaniline, known for a long time. But then I'm just going to polymerize aniline at the interface. So we have the anilinium, which is dissolved in water. And with the help of a graphene oxide monolayer, which can be stabilized at the interface, I take the anilinium close to the surface. So on the surface, I have this anilinium, which is available on the water surface, and then try to have electrochemistry just at the interface. The electrode is not dipped inside, but then just on the surface. And you have the other electrodes as usual. So this is something that leads to certain properties which are very different. Why is it that I'm just talking about this particular example? Polyaniline reactions are quite well known in the literature. One understands all these stages of polaronic, bipolaric form, the leucoemerald into phenylgranulin, things like that. But what's of interest is the polaronic and the bipolaric structure, wherein the polaronic structure has only benzenoid rings, while the bipolaric structure will have benzenoid and the quininoid rings. And they do have different conductivity. They do have different solubility. And there's been lots of interest in looking at the possibility of forming only the polaronic structure, for example. With that as a background, what we do actually is to polymerize it at the interface under pressure. So we have the aniline at the interface and compress, and subsequently it's polymerized at the interface. And after the polymer is formed, I characterize this. And this kind of characterizations are quite well known in the literature, but then there is a difference that's observed. What you see on the left is what we call as XC2 without any pressure applied. So you'd have 3 sets of redox peaks. And these redox peaks correspond to what I just mentioned earlier as leucoemerald into emeraldin, emerald into phenylgranulin, and then there is a quininoid structure. And that's what these 3 redox peaks are. But then when I try to have the polymerization under pressure, what you see on the right has only 2 redox signatures, 2 sets of redox signatures, where you do not have the quinone type of a redox property that is actually appearing. So what does that mean? You do have in situ, we have more like a polaronic structure, while when I just carry out the polymerization in the normal case, I have bipolaronic and the polaronic structure together. Of course, one can have this polymer put on a surface and then control the thickness and things like that. I particularly wanted you to look at this one because this thickness is important, because subsequently I'm just going to use this for actuation, electrochemical actuation purpose. And how do I know that I have a polaronic or the bipolaronic structure? Look at the Raman spectroscopy, both in situ and also ex situ Raman spectroscopy, and try looking at the outer plane bending modes. And what you see on the right is the benzenoid ring CH bending, versus the quinoid CH bending modes. And one can immediately see that the polaronic form and the bipolaronic form have different signatures. So when I have the polymerization happening under pressure, I do have the polaronic form, and when I do not have the pressure, it actually gives the bipolaronic structure as well. Now, I'm just going to play a video, and what you see here is an electrode, and in this electrode on this surface, I have polymerized the polyaniline under pressure, and I have the other two electrodes. And this is a substrate which is flexible. There's a flexible graphite on which the polymer is actually put on. So when I have something like this and then use this in an electrochemical system and then try to apply a potential, you just look at the actuation here. It's going from 0 to about 1 volt, and then it just comes back. So this kind of an actuation goes back and forth for almost 1,000, 1,500 times. And after that, you start to see a little change in the extent of actuation. Because one can also push the material, there's certain mass associated with that by applying a potential. Now, if I have a control experiment wherein the polymer is formed without any pressure, I do not really see this kind of an actuation. And I just have to mention that the previous case, I have the polymer formed only on one side, and it's possible to have the polymer on both sides and then try to do the actuation. It doesn't, because one side pulls this way and the other side it pulls the opposite direction, and it doesn't move at all. So this kind of an actuation is possible. What you see here is all at different potentials. You see that there's bending in the polaronic form, and in the bipolaronic form, it just doesn't happen. Because we try to understand as to why it happens, what it is, and quite a bit on scanning electrochemical microscopy and also impedance measurements. The AC measurements do give lots of information related to what happens as far as the intercalation is concerned. We do see that in the polaronic form. I will not go into details of everything except saying that the equivalent circuit for the electrochemical interface is different for the two different structures, polaronic and the bipolaronic structure. Essentially, we have the intercalation of ions and water molecules as we apply potential. And since it's a polaronic form, nice linear form, it's a directed electric field which leads to this kind of an actuation, while it doesn't happen in the bipolaronic structure. So this is one thing that we have been actually looking at in terms of reactions under surface pressure. I'm just going to switch gears and then go on to the next part of it, wherein I'll mention about organic systems. There's been plenty of work on looking at strain within the material, and related to inorganics, there's been a lot these days. And I would try to say that, okay, when there's some strain within the organic system as well, which possibly is the reason as to why it might work as a good electrode material for a battery. But before I just go on to the organic material, I just want to tell you, this is something that this is single crystal of molybdenum selenide telluride alloy, as you see here. And we do look at the strain in the system using Raman spectroscopy and understand this by what we call as a two-mode behavior, and see that even without any external pressure, just because I have changed some of the selenium to tellurium or sulfur to selenium, you have strain within the lattice. And my colleagues tell me that these could be good single photon emission materials, particularly sulfides and selenides in terms of tungsten and all that. So we try looking at some of them, and they're all nice single crystals grown using chemical vapor transport from elements using a transport agent. So they're very clean single phase material. I'll just go on to the organic part and then come back to the strain. The reason why I just mentioned about the molybdenum selenide telluride was it has strain in it. And it's a strain that leads to certain optoelectronic properties different from the N members. And that's been studied in the literature quite a bit. Now, why is it that I'm interested in an organic system and also the batteries? Plenty on lithium batteries, and there have been interests in other kinds of batteries as well, particularly when you have high valent ions, magnesium, zinc, aluminum, and things like that. So it's possible to have a slightly larger amount of energy that can be stored. We've been trying to look at magnesium, zinc, to some extent aluminum, which is not very easy. But then the reason as to why we are interested in it is what is actually given here. In terms of potentials, they're fairly high. If you look at what's for lithium as opposed to aluminum and magnesium, you have a fairly high energy density. But nothing comes for free anyway. Aluminum is not going to be easily reversible back and forth. Magnesium is difficult as well, simply because of the oxide formation and then coming back to it. But there have been studies on using inorganic cathode materials for magnesium as well as zinc in the literature. Very often what happens is, as you go on cycling, after some time it just comes down. The efficiency comes down and everything stops. And the reason is you can't reversibly intercalate and then deintercalate these metal ions. And organic systems can actually come in handy simply because the charge storage happens based on ion association. Ion association can be very fast. It's not intercalation, it is not conversion, or it's not alloying, which happens with inorganic materials. Very often when we have this kind of reactions happening in the inorganic materials, either it's a layered material or something like silicon where you have an alloying that's happening, there's a volume expansion, and many other aspects as well. They all come out to be initially okay, but then as you go along, they come down. So it's not easy for us to use it for a fairly long time. And that's when the organic systems have come in handy. But then the organic systems have their own issues simply because most of the organic molecules will dissolve in the solvents that we use for batteries. So one needs to find a compromise, and that's where people look at polymers. So the solubility in battery solvents is an issue as far as organic solvents are concerned, though it's known for quite a while. People have been looking at many different organic molecules, and it's possible to have the ion association or the storage happening, including high-valent ions like aluminum. So you have a fairly good storage capability, but however, it just stops at some point simply because it all goes into the solvent. So it's essential to look for certain polymers. And this is a polymer that was looked at, and this is a random copolymer. It's quite an amorphous material, easy to synthesize. Essentially what you have is a quinone and a pyrrole. Just put it in 2 beakers and then keep it in some under ambient conditions for a long time. So you leave it for a long time, and what happens is the pyrrole goes into the quinone, slowly diffuses, and you start to see the polymer. And it's possible to control the conditions and make sure that you don't have to be there for 48 hours and it can be reduced. And it's also possible to make composites out of it. And these polymers are having quinone as well as pyrrole as anchoring points for metal ions. And that's what we are trying to do here. So essentially, we try to understand how it actually happens, and there's a Diels-Alder reaction, the nucleophilic addition followed by a Diels-Alder reaction. We've been trying to see this particular thing based on mass, and that's still in the process. Okay? But once we have this kind of a polymer, we try to characterize the way we do, and the first thing that we look at is the solubility. It is not soluble in the battery solvents, and that's the basic advantage for us. So once we have that and then try to understand the electrochemical properties after looking at the physicochemical properties that are shown here. It, for some reason, forms like a layered structure, but then it's an amorphous material. It's possible to have it in a solvent and exfoliate it as well, and then have a thin sheet of this polymer formed. We try looking at this as an electrode material, and these electrode materials are used for many different ion storage. What I'm just showing you is a magnesium rechargeable battery. As I already mentioned, it's not easy to have magnesium and aluminum in the rechargeable mode simply because of the oxide formation and the reversibility being low. So what you see on the left is actually the ultimogram that gives you information on the magnesium interacting with the quinone part of it. And we do have quinone as well as the pyrrole part of it, which can participate in the ion association process. And what you see on the right is actually the stability, and fairly a good stability of about 1,000 cycles, and with a good stability. What you see on the right below, it doesn't really give the charge-discharge characteristics as an inorganic material. And this is something which is important to know, because organic systems will have a very different mechanism in terms of storage. I'm going to tell you what the mechanism is as we go along, and you do not really see a plateau as you see in inorganic systems. And typically people don't work with magnesium, they work with magnesium alloy. This is all aerospace alloys, which has certain aluminum and certain zinc, easily malleable, and one can actually process it nicely as opposed to just magnesium. So you do see a fairly good Coulombic efficiency of 98%. So the charge that you put in, the charge that you take out, no, it's not that bad. I mean, 98% is fairly good in some sense. What you see on the top is actually the rate of charge and discharge. Anytime we have a battery, it can be used in a toy, it can also be used in an automobile. So I need to be able to put in the charge and also the release the charge in different time scales. So essentially, I need to have a fast charge and discharge, slow charge and discharge, and that's what you're seeing on the top. You just have the fast charge and discharge coming down, and then again you take it back, more or less having capacity retention of about 100%. So fairly large number of cycles that happen, and these are essentially because of the polymer acting in a particular way. I'm just going to tell you as to why this performance. This is the performance that we see here based on certain electrochemical conditions. It's possible to look at the process that's responsible for the ion storage. This is what is called a pseudo-capacitive contribution. There's a capacitive action that happens when the ions interact with the polymer, and it is pseudo. It's non-Faradaic process in some sense. And what you see on the right is the impedance characteristics that gives you the phase angle associated with the interface, and it's all highly capacitive. You see most of them have about 45 degrees and above as the phase angle at frequencies of about 100 hertz or whatever. Now, why is that happening? I just mentioned about strain at the beginning, and I'm just going to say that, okay, strain is something that's important in organic systems as well. And if you have contortion, if you have strain in the system, there is a possibility of ion moving in and out fairly easily. At this stage, it's a hand-waving argument, and we still have to look at whether that is indeed the case. This is one example wherein strain gives certain properties which are very different from when I have just the planar surface. What you see in the middle is the molecular model of the molecule that is there on the left, which is about 23-degree contortion. And a similar system that was synthesized, which does not have contortion, does not have strain in the system, and that's purely planar. So the one on the right gives you a much, much smaller capacity as opposed to what you have with the strain. You just see this number, 700 farads versus 100 farad. So strain seems to play a role, or the defects seem to play a role in these cases as well. And at this stage, what one understands is the accessible surface for ion association and, okay, reduced pi-pi stacking and high molecular weight polymer. As I mentioned, I do not really have a proof for it at this stage, but yes, it is indeed one of the possible reasons. So the benzoquinone pyrrole polymer, if you try looking at the DFT, you have about 15 degrees. I have to caution at this point that all these calculations have been carried out with just one unit of the polymer, and I mentioned that it is an amorphous polymer. So there can be differences as well. But essentially what we have is a contortion which leads to this kind of a behavior. And this polymer, not only with the multivalent ion, you also have monovalent and trivalent ion that can be stored. And these are some of the characteristics of this polymer as a cathode for the lithium-ion battery and also zinc-ion battery, where you have a fairly large number of cycles that are happening. And they seem to be pretty stable and for a fairly long time. I think I'll just stop it at that stage and then get on to just the last few slides on this. Very often people do work on catalysis, electrocatalysis, and then make molecules and try and understand the catalytic property. And one way of doing it is have it on a surface, evaporate it on a surface as a film, and then try and understand what happens to the catalytic property. And I'm just going to say that one particular assembly, it's in this case phthalocyanin, and I'm just having an example of oxygen reduction. Oxygen reduction is pretty well required in many different processes. I just mentioned earlier, including corrosion and many other things, lithium-oxygen battery, metal-air battery, plus biological systems as well. There's been plenty of interest in forming hydrogen peroxide alone, not going all the way to water from oxygen. So is it possible to stop it at 2-electron, 2-proton process, not go all the way to 4-electron, 4-proton to have water? So essentially what's done here is, it's a very quick summary of this. So cobalt phthalocyanin is a molecule that is organized on the surface. And it's possible to organize it on a surface with the plane of the phthalocyanin either perpendicular to the surface or going towards the surface in a slanted way, or even go down further. So when I have the same catalytic molecule, catalyst, organized in two different ways, I have difference in thermodynamics and kinetics of the reaction that it catalyzes. And that is what this one is all about. Okay, before I just go on to the catalytic properties, we try to understand whether the orientation is indeed happening, and they again doing Raman and also electrochemical signatures that gives the coverage of the molecule on the surface, and the Raman gives you the orientation as well. And of course, one can also do polarization dependent IR, which gives the orientation. So it's possible to have the orientation of the molecule on a surface very precisely found out. It can be 23 degrees, 38, 45, or whatever it is. And this is used as a catalyst. In this particular case, oxygen reduction. The substrate is silver in both cases. You see that in one of the cases, the oxygen reduction gets catalyzed. The potential actually goes more towards the left, but then the current remains the same. It stops at that stage itself. But then when I have a slightly different orientation, a parallel orientation, what you see on the right is what is happening. The green one is on the bare surface, which is silver, and the blue one is actually in presence of the parallel oriented phthalocyanin. You start to see two peaks, and the first one is due to oxygen to peroxide, and the second one is due to peroxide to water. And when you intentionally add peroxide, you see that current goes up. That's the third one, red color one, which doesn't happen when the molecule is perpendicularly oriented. So there is an orientation-dependent catalysis, both thermodynamically and also kinetically. One can control the properties of it. I will not go into details of this. I probably will just close the talk at this stage, and thank you very much for your attention.